Guys, let's start. The fourth lesson in the course Code Refactoring is about some principles, especially object-oriented programming principles, but I think that we can use them in a functional programming. The first principle, or maybe even methodology, it's inversion of control. I hope that you already saw or listened something about this principle, but if it's not, it's a normal because it's hard. So, inversion of control, it's when the flow of control is reversed. Usually, your code calls a library or another class. For example, here in this slide, I have two examples of code. In the left, here we have some class game with method run, and inside this method we just create new objects and call some methods of this object. And usually we just call some methods and that's all. With inversion of control, something else calls our code instead. And in the right example, we can see the player with some methods, and the framework calls these methods at the right time. We need just implement these methods and add some logic inside it. This principle, when we use inversion of control, can help make our code cleaner and easier to change. Inversion of control often used in frameworks, event-based systems, and when we work with dependency injection. Especially dependency injection, it's an example of implementation of inversion of control. When we use inversion of control, we don't control everything. We give control to a framework or some high-level system. And it helps us write flexible and testable code. For example, guys who studied in the previous year in mobile application development, I hope you remember that in Android we have activities with special life cycle, and it's an example of inversion of control, because operation system run everything, run the methods of activity. We just need to implement these methods, and operation system will decide everything will run in the correct time, and we don't decide anything. And this principle, inversion of control, it's a main part which allows us to separate libraries and frameworks. When we talk about libraries, we control everything. We just call the methods of library. When we talk about the framework controls us and our code, and framework calls our methods, which we implement. Usually when we create some user interface systems, like in Android, in iOS, in front end, we use frameworks. And frameworks control the life cycle of objects in the screen. When we just use some little instrument which allows us to draw something or another, we talk about libraries, because a library doesn't control us. It just gives us the ability to make something easier, and that's all. I hope it's clear. The next, it's a solid principles, And some of you maybe already knows about it, but if you don't, I think it's very useful to remember it. Uh, these principles, when applied together, can increase the reliability of our system and maintainability to add some new features. Solid principles are some guidelines that can be applied not only for programs in object-oriented programming, but I think for all programs, for all programming languages. And it's better to use them. So let me explain you all principles in this group. First principle, it's a single responsibility principle, and it means a class should have only one reason to change. In simple words, a class should do only one job. We can use this principle for class, for method, because I already told you that method should do one thing. It's the same. Maybe for model or some part of your system. And why is that important? If a class has many responsibilities, like saving files, showing data, or save something to database, that it becomes complex, hard to change, and easy to break. Like in this picture, we see a Swiss Army knife. So class, it's not a Swiss Army knife because it has too many tools in one place. We don't want our code to look like this Swiss Army knife. And also, we need to look at who use the class. We call them actors or stakeholders. And if many different types of users depend on the same class, they may want to change the class in different ways and for different reasons. That's a warning sign because even if the class looks small, it might have too many responsibilities because it's serving too many masters. So this principle is about how many people or system can affect the class. If these actors have different needs, you should split the class. This keeps your design clean, stable, and easy to maintain. I think it's maybe the most simple principle. The next one, it's the open-closed principle, the second principle, and it says software entities should be open for execution, for extension, but closed for modification. It means that your classes and function should allow new behavior without changing existing code. You can extend the code, but you should not have to edit the old code to add new features. Let me help you show you the example. In the left side, we have bad code without this principle, and in the right, we have the correct code with open-closed principle. And every time we want to add a new payment type in the left piece of code, we have to modify this class, adding more if or switch. This violates the open-close principle because the class is open for modification. It's bad. In the right side, we can see the correct code, and we can add new payment type by just creating new class. We don't touch existing code. The payment processor class will be the same. We just extend the system. It's important because when we modify our code, we can add some errors. But when we extend it and create new, I think we will not add some bugs if we don't want to do it. So the next principle, it's Liskov substitution principle, and it says subtypes must be substitutable for their base types. In simple words, if class B extends class A, you should be able to use B instead of A, and the program should still work correctly. Look at the image. You can see a real duck and the rubber duck. They both look like ducks, but the rubber one needs batteries to work. It's not a real duck, it breaks expectations. In code, we can create the same problems. Let me show you the example. Again, in the left side, I have the bad code, and in the right, the correct. Here we have a base class called bird, and it has a method called fly. But if we will create the subclass called penguin, because penguin is a kind of bird, but there is a problem because penguins can't fly. This breaks Liskov substitution principle because we can't safely replace a bird with a penguin. Someone expects that all birds can fly, but the penguin throws an error. This is like saying a rubber duck is a real duck, but it needs batteries. So we need to fix it. And in the right side you can see how we can fix. We separate birds that can fly from birds that cannot. We make interface flying bird and only flying birds like sparrow or eagle implemented. That way we don't trick the system. So no errors and no surprises. The next principle, it's an interface segregation principle, and clients should not be forced to depend on methods they do not use. I think it's hard to understand, but it's very simple. Each class should only be connected to the methods it really needs. If we give a class an interface with many methods, but it only needs one, then the class is forced to know too much. And this makes the code more complex, harder to understand, and harder to change later. Let me show you the example. Let's imagine that we create the application, mobile or maybe web, for chatting. And we create the interface, chat channel, for all channels in our chat. And we add a lot of methods inside this interface. Then we implement this interface, and we have a lot of classes. For example, group, which need only load messages, send messages, replies to messages, and forward messages method. Another method we don't need in this class. The same for secret chat, channel, and supergroup. Every class has a problem because it does not need all methods from chat channel interface. And it can be the reason of problems. We should split big interfaces into smaller ones, so each class only depends on what it uses. This keeps the system clean, focused, and easy to maintain. It's better to create a lot of little interfaces and use them if we need them. And the last, but the most complex principle, it's a dependency inversion. It's another example of inversion of control. And you can read the text about this principle in the slide, but I think it sounds very complex. So let's make it simple. Let's imagine that we have the system with some classes or maybe models inside it, and in this scheme we have the dependencies between these classes. Let it be classes. We have class E, and class B depends from class E, and class A depends from class B. And if we will change something in a class E, it means that we should change the class B, and then we need to change the class A. But what if the class E it's not stable and the developers change it every day? It means that we need to change the half of our system every day. I don't like it. I'm too lazy to do it. That's why I want to use dependency inversion principle. I want to change this dependency and reverse it. How to do it? I create the interface and my class B works not with E object but with realization of this interface, and class E should implement this interface. And in such structure I reverse the dependency because interface it's a part of this class, and now class B controls the class E and tells to the class what method should be inside this class because of this interface. And the same, for example, for class C and E. We added interface here as a part of class C, and our dependency reversed. And now class E depends from this interface because in this interface we store the contract which is important for class E. Class E should implement this contract. Maybe another example, but with these strange classes. Class foo depends from class bar, and I need to change this situation. I add the interface, and now this class work with this interface, and class bar should implement this interface. And the most important part that this interface should be close to class foo. It should be in the same model, in the same folder, maybe even in the same file. But because if we will not connect these two elements, we will not reverse our dependency. So that's important that this interface is near class foo. I hope it's clear. And when you will make your laboratory project number 1, you can find the violation of these principles, solid I mean, and I will give you more points if you will find something like this. Another principles, solid it's not only one principle of object-oriented programming, we have more, and I hope that you know these principles. And they help us write clean and maintainable code. Dry it's don't repeat yourself, kiss it's keep it simple stupid, and law of Demeter, I think that you don't know what is it, but its principle talk only to your direct friends. So let's look each of these one by one with simple examples. Dry or don't repeat yourself says that each piece of knowledge should have a single consistent representation within the system. It means that don't duplicate the same logic, the same data or rules in multiple places. If you do and you need to change something, you have to change it everywhere, and it can be a reason of bugs. When you follow don't repeat yourself, your system becomes cleaner and easier to maintain. But sometimes we need to violate this principle, and we call it wet. We enjoy typing and sometimes it's necessary. For example, in multiplayer client-server games, both sides may need to repeat the same calculations because the internet connection can be not so good, but we need the speed. That's why we calculate in each sites. Or, for example, in data validation, if we check the same input in the client and in the server for safety or better user experience. In these two situations, we violate dry principle, and it's normal. Because don't repeat yourself, it's a guideline, not a law. We can use it to avoid unnecessary repetition, but be smart about where and why repetition happens. Another principle, it's a KISS, or keep it simple stupid, or maybe keep it simple and stupid, or maybe so this principle have a lot of meaning. And don't make your code more complicated than it needs to be. Simple code is easy to read, easy to test, easy to fix, and you don't need some clever solution. You need a clear one, understandable for everyone. When you're writing the code, please always ask yourself, is this the simplest way to solve the problem? But remember that simple is not the same as primitive. Good design should be simple, but and that's all, just simple. And the law of Demeter. I think I need to check the attendance and make a screenshot. Wait a minute, please.
Okay, man.
Okay. So the law of Demeter. It's also called the principle of least knowledge. It means that a model should not need to know the internal structure of the objects it works with. In the other words, talk only to your direct contacts, not to their contacts. And the law of Demeter has very formal list of rules, and you can read it. That some method of class can call methods only the following objects, like the methods of the same class, objects which created by this method, objects which pass as a parameters, and objects which is fields of this C class. But only these objects, and that's all. Let's check this little example. Here I have the class seller and special object price calculator as a field of this seller. And here I have the method sell with some parameters, and inside this method I have violation of law of Demeter. So in previous slide we have the list methods of C, objects which created, objects pass of parameters, and fields. So here I create object actual sum and save the result of wallet get money inside it. It means that inside this variable I will have wallet get money. I will have the money inside this actual sum. Again, I create required sum, and here I store the result of calculation, the sum of products, and now I need to check is the actual sum is less than required sum or not. And here I have the violation of law of Demeter because I try to call the method of wallet get money. I can replace this actual sum with wallet.getMoney.isLess than. but money it's not the friend of our method. That's why we can't call it. I Maybe you see to this code and don't understand why it's bad when our seller uh, just call the method of money class. Maybe it's normal, but let's think in another way. Imagine that you come to the store and you want to buy something, and you see the seller, and to buy something you need to get your wallet to the seller. I think it's very strange. It's not it's unsecure because you just give all your information, all your documents, all your banking cards and money to your seller. You don't know this person. Why you uh, uh, why you do this? It's strange when we think in real life, and in the code it's strange too, because the seller knows about money and run this method of money class. It creates extra dependency between seller and money, but we don't need this dependency. The law of Demeter, it's about extra dependencies. Our goal is to decrease the count of dependencies inside our application, because when we have a little count of dependencies, when we change something, we will not need to change a lot of code. But if we will have a lot of dependencies, sometimes we need to change the whole system. That's why law of Demeter give us information, give us the rule with which method we can work in our method. And here we violate this law here and here because we call the methods of money class. And we can change this code to remove this extra dependency. And now we have the sell method, but we use money like parameter, not wallet. And I think it's close to real life, because when we come to store and want to buy something, we give our money to the seller, not wallet. To give the wallet is very strange. And now we have not any violation of this principle inside this code, because in method sell we works only with money. We don't know anything about wallet because we just don't need this information. And now we have the dependency between seller and money, but we have not any dependencies between seller and wallet because we don't need it. We don't want to know anything about this class because we are too lazy and we don't don't want to know extra information. And when we don't want to know something extra, we can talk about abstraction. In object-oriented programming, we have three famous principles like inheritance, polymorphism, and encapsulation. But abstraction is very important too. But sometimes we don't remember about it, and it's sad because it's very important. Abstraction means that we focus on the important details and hide everything else. In the first lesson, I already told you that a human can remember only 7 things in one time, not more than 7. Abstraction helps us to reduce the number of things which we need to store in our memory. That's why it's so important. I don't want to think about it. I just want to use some method and that's all. When I create the mobile application, I don't want to think about how to download the image from the server. I just want to run one method with a link to the image as a parameter, and that's all. It's an abstraction, and it's a lazy laziness. So we focus on the important details, and only these details what we need. In programming, abstraction helps us work with objects or systems by showing only the necessary parts and hiding the complex internal stuff. We work with very complex system, and if we will try to know about everything in our systems, I think we will have a lot of brain problems. That's why use abstraction. For example, when you use a list that's like type of variable, you don't care how it stores items. Is it array, or maybe it's or maybe something another? You just add items or remove them. You don't interest in what it how it store these items. Abstraction makes our code cleaner, easier to use, and less dependent on changes inside. So always ask yourself, what details do I really need here? And everything else can stay hidden. Uh, Balance is a key to good programming, to quality code, to clean code, because abstraction is powerful, but it must be used wisely. If you don't use enough abstraction, your code may come too specific and tightly connected. Later, when the project grows, you will hit architectural limits. So you need to do painful refactoring, and you add quick fixes and workarounds. So it means that you cost time, money, and nerves. But if your abstraction is too deep and too generic, you get something called over engineering. That means that your system becomes too complex, hard to understand, hard to change. Also, you might build flexibility you never need, just in case. Sometimes we use some patterns to make our code more flexible than we need, and it's a bad idea. Uh, because then even small changes require extra work just to satisfy this architecture. That's why the key is find the right level of abstraction for your real needs. Not too little, not too much, and good abstraction saves effort. Too much or too little can bring pain and cost. Let's remember about another principles of OOP, because sometimes students think that they know what is it, but it's not true. And polymorphism, it's a feature of system that allows you to have many different implementations of the same interface. I tell you about it because it's a very famous question in interviews. For example, when you will try to find a workplace, interviewer can ask you what is polymorphism, what is encapsulation, and moreover. That's why I try to help you. Uh, you can write code that works with the interface and then use different objects behind it without changing the main logic. Like in this picture, we have a lot of animals or birds, and every animal can make a sound. We just call the make a sound method, and the result depends from the type of animal, but we don't know about it. We just know that we have some animal with method make a sound. The next principle, it's encapsulation. It means we control access to the data and behavior of an object. We don't just hide the data, we also wrap it into one place inside the object, like capsule, because encapsulation. This object decides what is public and what stays private. This is good because it protects internal data from being changed in the wrong way. It let us change the inside of the object without breaking other code, and it keeps the object behavior clear and safe. And abstraction is very close to encapsulation, but they are different. Abstractions means that you can view the object from a general point of view. You only see the important parts, not the internal details. Here, you can see the door to the house, but you don't know what is made of. Encapsulation means another, that you cannot view the object from a different perspective. The object hides everything inside and controls how you use it. So, abstraction is about showing only what matters. Encapsulation is about protecting what's inside. These two animals, maybe it's bears. One is kind and one is angry. They work together. Abstraction gives you the idea, and encapsulation makes sure that you use this idea safety. And the last principle for today, it's inheritance. It's a system feature that allows one class to inherit properties and behavior from another class. In simple words, one class gets the code of another and can expand or change it. But inheritance is not always safe. I shown you the Liskov principle, and if we change the child class in the wrong way, we can break the parent-child relationship and create violation of Liskov substitution principle. Deep inheritance chains can make code hard to understand, hard to test, and easy to break. That's why, in many cases, it's better to use composition instead of inheritance. If you don't remember what is composition, it's when we store the object of another class in one class. In object of another class, of course. If you don't sure that you need the inheritance in some reason, use composition and it will be better solution. Use inheritance only when there is a clear relationship, which we called is a. It means that the objects are the same, like animal and dog. Dog, it's an animal. That's why we can create the inheritance between these two objects. If you have another relationship, like has a, like tail, it's a part of dog, use composition. And it will be more flexible, safer, and easier to control everything. So it's the last slide for today. Maybe you have some questions.